This lecture is called The Bigger You Are, the Harder You Fall, and this is an introduction to gravitational potential energy. You have a quote by President Barack Obama who says, "We need to steer clear of this poverty of ambition where people want to drive fancy cars and wear nice clothes and live in nice apartments, but do not want to work hard to accomplish these things. Everyone should reach their full potential." And we are talking about potential energy in this particular case. So, the goals are that for this lecture that you be able to identify the factors that affect gravitational potential energy. Also that you should be able to relate work and gravitational potential energy. And you should be able to use the formula PEG, which stands for gravitational potential energy, equals mgh, which is mass, gravity, and height. So, it's all about potential. So, if you take a book and you raise it to a greater height, it actually results in a bigger thud whenever you release it and hit the ground. If you have it here, it barely makes a sound, gets a little louder, and finally you have a giant thud whenever you release it from there. It's because the energy of the book has to be transferred to the ground, and it's actually transferred via the vibrations, which we now know as sound. So the more energy it has to transfer, the more energy that is transferred to sound, the louder the sound that you hear it. Okay, so it's one of those things that as you increase the height of the book above the ground, all of a sudden you have more energy that you're dealing with. Okay. Additionally, if you increase the mass from a same height. So if you drop a single book from a height of 1 meter, it makes a certain amount of noise. But if you were to stack 2 or 3 books, it would make a greater thud. And if you were to stack 5, 6, 7 books, it makes an even louder thud. So once again, you have more energy that's being transferred to sound, so you make a louder noise. So if you increase the mass of an object, it also results in a greater impact. So what that actually leads us to is what we now know as PEG equals mgh. This stands for gravitational potential energy. And what it represents is it's the energy that's stored in an object due to its position. You have mg, which is mass and gravity and height. Now we talked specifically about the mass and height terms. We didn't talk about the gravity term because it's not a term that we can easily manipulate on Earth. The gravity on Earth is 9.8 and it doesn't really change from there. So you have right here mass, which is measured in kilograms. You've got acceleration due to gravity, which is meters per second squared. And you have height, which is m. Unless it says otherwise, you can assume that gravity is going to be 9.8 because it's on Earth. Now, if it says on another planet or something along those lines, you can no longer make that assumption, but you can do that. I do want to show you where this equation came from, and it came from this right here, where if you were to take a look at this particular expression and erase what we've got right here and kind of group it a little bit differently, height, remember, is another term for distance. It's a vertical distance term. But that's what height is. If you were to group mass and gravity together, or mass and acceleration, make a force. And then potential energy is a type of energy which can be seen as work. So what you're looking at is the gravitational potential energy formula is just our work equation going in the vertical direction. So work equals force times distance, or potential energy is equal to mass times gravity times height. And it makes sense with the law of conservation of energy. If you take a box and pick it up off the ground, you're exerting a force over a certain distance. The law of conservation of energy means that whenever it gets up to here, it's got to have the same potential energy of work that you put on the box. So those two things are equivalent. So in the second one, we said work is equal to the change in kinetic energy. Yes, but work is also equal to the change in potential energy as well, because if you lift the box up with a certain amount of work, it's going to gain that much potential energy as well. So if we look at our example, we say work is the same thing as gravitational potential energy. Okay, it's the same thing. This force gets expanded into mg, and this distance is just another way of saying height. You've got to know that the law of conservation of energy is going to apply to every energy that we talk about. So, example A1 says an object has 200 joules of potential energy when suspended 8 meters above the surface of the Earth. The same object is suspended 5 meters above the surface of an alien planet. It has 5,000 joules of potential. What is the gravity on the unknown alien planet? So what I'm trying to solve for is the gravity on the alien planet. Okay? It says this, so let's start over. We have a 200 joules of potential when suspended 8 meters above Earth. So I'm going to have two columns here. I'm going to have Earth and I'm going to have alien. And on Earth, I know that gravity is 9.8. I also know that I have 200 joules of potential, so PEG is 200, and I know that the height is 8 meters. Okay. On the alien planet, I know that I have 5,000 joules of potential, and I know that it's suspended 5 meters above the surface of the Earth. So one thing that you should realize right away is if I'm trying to solve for the gravity on the unknown planet, I should only use the variables from the alien planet. I shouldn't use anything from Earth. Okay, except for one thing. It says the same object. So one of the things that you should have learned from force is that when you have an object with a certain mass and you move it somewhere else, the mass does not change. Only the weight changes, not the mass. So if I can solve for the mass of the object using Earth, I can get that same mass for the alien planet, and then I can go ahead and I can solve for the gravity on this unknown planet. So that's what I'm going to do. I'm going to go ahead and say Earth, and I'm going to do it up here at the top, kind of running out of room a little bit, but I'm going to say 200 equals the mass of this unknown object times 9.8 times 8. I'm going to divide both sides by 9.8 times 8, and when I do that, I end up getting the mass of the object is 2.55 kilograms, which now I can go apply to the alien planet. Now I'm going to change colors for the alien planet just so that we can distinguish between the two. So now I know I've got 5,000 joules of energy. I know I have a mass of 2.55 because mass never changes. I can solve for the gravity because I know that the height is 5. I would divide both sides by 2.55 times 5, making sure that I'm using parentheses or solving for the number to begin with. And when I do that, I end up with the gravity being a very large number of something around 392 meters per second squared, which is a very, very, very large number. You're talking about something that's, 40 times the gravity of Earth. Okay, this is a really hard question for a couple of reasons. Number one, you've got to use the formula to solve for gravity, which most people assume is always 9.8. You've got to look for key things like alien planet. You had to use the stuff on Earth first to solve for the mass, and then use the mass to solve for it again. So it's a two-step question in addition to solving for the gravitation. So it's a tough question, but it's something that you need to be able to do. What height should a 50 kilogram box be raised above the surface of the Earth to give it 2,500 joules of potential energy? So we're looking for the height. It says a 50 kilogram box, 2,500 joules of potential energy, and you're looking for, and then the key thing is Earth. So I can say that the mass is 50 kilograms. I can say that the gravity is 9.8 meters per second squared. And then I can say that the height, which is what I'm trying to solve for, and I know that PEG is 2,500 joules. So I can plug into the equation PEG equals mgh. I'm going to go ahead and solve for it algebraically this time, just to kind of change it up a little bit. I'm going to divide both sides by mg, and when you divide both sides by mg, you get the height is equal to PEG divided by mg. In other words, the gravitational potential energy divided by the weight, because remember mg is the weight, is equal to the height. So I can say 2,500 divided by 50 times 9.8. Remember that we have to do that first. It's in parentheses. Would be 490. Just go ahead and write it underneath just so we know. Is equal to the height. And when you take 2,500 and you divide it by 490, you get a height of 5.1 meters. Okay, you have to be very careful with your parentheses again to make sure that you get the correct answer. You should be able to kind of say, look, that doesn't look right. It's too high for what I've got. So make sure that you're being careful with parentheses in your calculator. The last question says, what is the gravitational potential energy of a 5 kilogram book held 10 meters above the surface of the Earth? Okay, Earth being there. So I'm looking for the gravitational potential energy, or I'm looking for PEG. Okay, I know that the mass of the book is 5 kilograms. I know that it was held 10 meters above the surface of the Earth. And I know that it's Earth, so gravity is 9.8. So I can use the equation PEG equals mgh, or in our case, it'd be 5 times 9.8 times 10, which would give me 490 joules. It would be my gravitational potential energy. Just so you know, another way that I could have said this is how much work needs to be done on a book to lift it 10 meters above the surface of the Earth. Because remember, gravitational potential energy is the same as the work done in lifting it.